Okay, let's get started. So last week of classes here. Today we will discuss test number 3 a little bit. We will hopefully finish up the multinomial regression section. And also just as a reminder, please remember to complete both course evaluations that are out there. The regular one that's due on December, I don't know how that date got removed there, but on Saturday it's due at 1 p.m. At least when I checked yesterday morning when I was preparing for our class here today, 5 of 9 students had submitted theirs. And also, of course, my evaluation is due tomorrow at 5 p.m. And again, all you need to do is do that first question in order to get full credit if you choose not to respond to any of the other questions. So, is there anything you'd like to discuss before we talk about the tests? Okay, so here's just a posting of the grade distribution as I had posted to the discussion board. There was some obviously variation in the grades. There's a few problems that I want to talk about so that hopefully if you see similar problems like this on the final exam, it will not cause you difficulty. So number 1A, I wasn't anticipating the issues that some students were having here. So we have these 4 observations, and we need to use nearest neighbor classification for these 4 observations. Where some students misunderstood was that they thought it was nearest neighbor cluster analysis. Obviously, the name nearest or the phrase nearest neighbor is shared by both, but this is nearest neighbor classification. What are some things to think about here in order to make that choice, if that is the correct thing? Well, we have this k equal 2 there. If it was nearest neighbor hierarchical clustering, you wouldn't have a k equal 2 there. I give the actual groupings for the variables already, so it wouldn't really make sense to do a cluster analysis unless I told you something different, which I do in part C. So this unfortunately threw some students off, and the problem was worth 10 points. And if you were using nearest neighbor cluster analysis, I took off 7 points and moved on to grading the next problem. I didn't think there was necessarily a better way to do it because you're totally doing a different method. And so I guess in this particular case, the thing that I want to get through is that, be careful about applying the correct method. When we were talking about cluster analysis, we don't know what groups, what populations the observations come from. When we're using nearest neighbor classification, or discriminant analysis, or just regression, or multinomial regression, we know what the groupings, what the populations are beforehand. And, even like, for example, right here, we're using resubstitution. Well, there's no way you could use resubstitution with cluster analysis. Okay, so let's move on to C. Then I say, okay, well, now ignore it. Ignore what populations that the observations come from. Now we could or we can use cluster analysis in this particular case. And in this particular case, we're using the furthest neighbor method. And there ended up being 3 steps here. The first step, I think pretty much everyone got right. And that is, look for the smallest distance between 2 observations, and those 2 observations then are joined together for the cluster. Now, the next step, though, is where there were at times differences in how students responded, in terms of some, unfortunately, got it wrong. And I do anticipate this. I've seen this issue before, and the key is that sometimes students think, okay, I'm always looking at the shortest distance. I'm always looking at the shortest distance. I'm always looking for the shortest distance. And you are, But the key is understanding how you define distance. And once we have a cluster, that's when the name furthest neighbor comes into play. So in this particular case, so we have a cluster that has 1 and 2 in it. Okay, we need to find the distance between 1 and 2 and then observation 3. If I'm using furthest neighbor, I look at, okay, I'm going to look at, let me do a little bit of erasing here. So if I'm using furthest neighbor, then I look at the distance between 1 and 3 and 2 and 3 to make the decision about what's the distance between the cluster that has 1 and 2 in it and then the distance to 3. Furthest neighbor means you take the largest distance. And so because of that, the distance between 1 and 3 is 7.21. In a similar manner, the distance between the cluster with 1 and 2 and 4 in it, oops, let's see here. The distance between the cluster that has 1 and 2 in it and observation 4 is not 4.12, it's 7.07 because it's the furthest neighbor. And so when we look at then a table now that has all these distances in it, you look for the smallest one now, and that is joining 1 and 2 to 4. Okay? Okay, let me get back here. 1 or 2b. So I tried to make this a little bit simpler for you, where you didn't need to go through all the calculations. Obviously, you're under time constraints. So I'm asking you on this particular problem, just show me that you understand what essentially Mahalanobis distance looks like, and that you could set up the equation. And so there are some calculations, but not the full calculations that would be needed. And on this particular problem, I was sometimes having students do the posterior probabilities, which in the end usually didn't cause anybody any problems because you need the Mahalanobis distances first to get the posterior probabilities. But obviously, in terms of time constraints for the test, that's going to take time to do that extra part there. And so you didn't need to do the posterior probabilities. I didn't take off points for it, as long as you still show me what the Mahalanobis distance was. But then I was having some students using the linear discriminant rule, which is not asked for in this particular case at all. Now, why did that occur? I would hypothesize the reasons because they saw my code that was in my program. In my program, I had the linear distance rule, then I had Mahalanobis distance, then I had posterior probability. So, it was a copy-paste, and for some reason, one chooses to work with the linear discriminant rule more than the Mahalanobis distance. And so, if you still gave me the Mahalanobis distance, that's fine. I'll give you credit for it. But if you only give me the linear discriminant rule, then you didn't do what the problem asks. And so, unfortunately, points had to be deducted. (3c). So we had this ROC curve. Yeah, I wanted a discussion about, okay, how did I word it here? Advantages and disadvantages of 0.1 versus 0.2. And so the purpose of this problem was to give to show me that you have a general understanding what ROC curve is. And so what most students did was that they approach it from, okay, well, obviously one's going to have low sensitivity, but high specificity, and number 2 is going to have high sensitivity, but lower specificity. And a lot of students just left it at that. And I gave you full credit if you did that. But what would have been nice is if you went maybe one little step farther and talk about in terms of the actual problem itself, in terms of people that are going to survive or people who are going to die with using either 0.1 or 2 to make those judgments. And so that's what I was hoping to see a little bit more, but Yeah, and it was fine if you you did not receive points off if you didn't go that far. And lastly, I'll just mention 4B. This was a problem that I really like because it gets at the intuitiveness for what we're doing with these methods that are trying to predict observations in groups. You know, the closer that the observations from, let's say, group 1 and 2 are together, the more difficult any kind of procedure is going to have in differentiating between those observations in terms of what groups that they belong to. The farther apart they are, the better the methods will work. And so that's the purpose of doing this. There was a number of practice problems that were focused on this as well. So I really like this particular problem. I think most students were fine on part I. Part 2, sometimes students had difficulty with understanding what happens with the variability. Okay. So that was just really briefly some things that I wanted to point out with respect to the exam to hopefully help you then with the upcoming final. Are there any questions about the test? Okay. Well, let's see if we can finish up multinomial regression today. So this is what a multinomial regression model looks like, just to review. I've written it just in terms of one independent variable, just to make it a little bit easier to see. And the key is on the left side, well, I guess first of all I should say, notice we have capital J minus 1 different lines to a model, which is something that you may not have seen before in a class or in any other stat course before, or any other course that uses statistics, where typically you just write one line for your model. Here we have multiple lines, where capital J corresponds to the number of groups that we have or populations that we have for our particular variables. We have capital J minus 1 of these lines to our model. And on the left side here, we have a log, natural log, and we look at probability of being in a particular group, let's call it little j, divided by the probability of being in group 1. And we do this for group 2, group 3, all the way to group capital J. And so what this is called on the left side are called baseline category logits. The reason why logit is used is because when we looked at logistic regression models before, when we had, let's say, the logit of pi, we had the log of pi over 1 minus pi. And so essentially, this is like category, let's say, 2. The probability of being category 2. This is like probability of being category 1. And so we have a very similar form here, so that's why the logit name is used. Baseline category, that name is used because we're always making a comparison to category 1. Now, in the end, as you saw from our last Tuesday, just because we're comparing to category 1 doesn't mean is not going to cause us any problems, because simply I could compare, let's say, category 2 to 3 by simply subtracting these two equations. And I just have a different way of rewriting my model. Now, on the right side of the model, we have our typical regression look to it, where we have a linear combination of the betas with our independent variables. In this case, just one independent variable. But we also have two subscripts on each of the betas. So our normal subscript here is that 0 and also that 1 that you would typically see in a regression model. So 0 corresponds to the intercept, 1 corresponds to, let's say, the first independent variable. But then we have a second subscript here, and that just simply corresponds to, well, which of these pi's you're talking about. So is it the second one? Is it the third one? I could more compactly state my model if I wanted to, like this, where I put the little j equal 2 to capital J in it. Now, using this model format, we have a way, and I do expect you to understand how to actually prove this. We have a way of coming up with, well, what would pi 1 be? And what would pi sub little j be for little j equal 2 to capital J? And it just ends up using some algebra to do this. I could ask you a question on the test to actually prove something like this. And so if I have these pi's then, now I know essentially, after let's say I estimate the model and I estimate these pi's, I have a way of judging, okay, should this particular observation be category 1, 2, 3, or whatever other category I have by looking at these pi's. The pi that is the highest could be a way then that corresponds to which category I predict for that particular observation, or what group I predict for. Okay? So that's just a really brief review. Last time we left off in the middle of this example that dealt with weak kernels. And the purpose here was we wanted to use some measurements on these weak kernels to predict the correct group for them. Are they healthy? Are they scab? Or are they sprout? So we have like 275 observations that we're going to use with a multinomial regression model to help us do this. And last time we were taking a look at basically some initial summaries of the data corresponding to stuff that we've done earlier in the semester for multivariate data. And so, for example, this parallel coordinates plot shows us the scab in green seems to differ the most from the other two groupings for these kernels. We can see it in terms of the density, we can see it in terms of the weight, size. They seem to can often have lower values. And so when you see something like this, then that says, okay, maybe some kind of statistical method could be used to differentiate or predict the corresponding groupings and predict it well. Okay. So the next thing then that we can do is to continue applying some stuff that we've learned before so we can learn some more about our data before we apply a multinomial regression model. And so what I'm going to do here is use principal component analysis so that I can view the data in maybe 2 or 3 dimensions. And we've seen this code before, so I won't go through all the details. We'll just do the highlights here of the results. So I use printcomp for this. If we look at the standard deviation row, what this shows me is that the first 2 principal components have a variance or standard deviation that is greater than or equal to 1. So using one of the criteria that we've used before, hey, 2 principal components might be good enough. I tend to more look at the proportion of the variation that's explained. And we can see with 2 principal components, I'm about 65%. I like to be a little bit higher personally. And we can see if I go up to 3 principal components, I'm up to 80%. Okay. We can also look at the loadings if we wanted to, or what each of the principal components represent. So principal component number 1, well, it's a contrast. It's contrast between all the variables in comparison to the hardness. Perhaps somebody who's really into grain science could interpret that. The second principal component, again, is a contrast between the density, hardness, size, and weight versus the moisture and whether or not it's hard red winter wheat or soft red winter wheat. That's what the class variable corresponds to. I should also point out now, the class variable itself is categorical in nature, has values of HRW for hard red winter wheat and SRW for soft red winter wheat. I need to make it a numerical variable in order to, of course, do math with it, to do principal component analysis with it. So I use an if-else function to help me transform it to a 1 or a 0. Okay, so let's look at plots of the principal component scores. So the plot on the left there is just for the first two principal components. And we can see again for the scab, which is in green, we see that there is some differentiating between them and the healthy and the sprout. And so when you see something like that, again, that says to me, oh, even though I'm only looking at maybe 65% of the total information, the data, that I might be able to use this data to help differentiate at least between scab and the other two groupings. And so we like to see this. I mean, in fact, what we would prefer to see, maybe I could ask you that on a question on exam, is we would prefer to see to see them more separated. Because the more separation there is, the better the methods will work. Now, I am, though, concerned, though, about will I be able to differentiate between healthy and sprout? You know, we see a lot of overlap there. Now, in the parallel coordinates plot, we saw something similar, although there were some variables that maybe there was a little bit of separation, not to the same extreme as what we saw with scab, but we saw maybe a little bit. Now, you might be wondering, well, why do I have this kind of a separation between these two areas right there? And that simply ends up being due to hard red winter wheat or soft red winter wheat. And in the end, it doesn't really affect our analysis at all. But that's where that's coming from. Now, when I add a third dimension by using a bubble plot, at least from that bubble plot, it's really hard to see much. And if I look at the three-dimensional scatter plot, okay, so if you look up here and as I move this around, we can again see the different, and I should have chosen green for the plotting points, but we can see kind of that indeed that the scab is somewhat different from the healthy and sprout. But what we can see here also is a little bit of differences between the healthy and sprout. Now, where? Okay. Now, remember that, okay, let me just remind myself. So, sprout is red, healthy is black. Now, notice if I look at the bottom, below the, I guess, the zero plane, notice how the reds tend to go a little bit farther down than the blacks. And if you look above the 0, 0 plane, notice how the blacks tend to go a little bit higher than the reds. Okay? So because of that, then you might be thinking, oh, well, maybe I will be able to differentiate between healthy and healthy and sprout somewhat. Probably not perfectly, but at least I'll have some, let's say, predictive power. And so anyway, so this is the kind of stuff that you would want to do before you formally then implement the methods that we've been talking about for the last few weeks. Multinomial regression, or you could use discriminant analysis. You could use nearest neighbor classification as well. You want to use the methods that we looked at earlier in the semester to get a general sense first, to have some ideas, and then you can go ahead and apply the corresponding methods that we're talking about now. Okay. So this is the model that I would like to estimate. The log of pi sub j divided by pi sub 1. And then I'm going to put all my independent variables on the right side, linear combination with the betas. Now, we have this j here. Little j is going to be 2 or 3. And you might be wondering, okay, well, I've only talked about healthy, scab, and sprout. How am I going to differentiate between should j equal 1 be healthy, should it be scab, should it be sprout? How do I make that designation? Well, it all comes down to how R approaches this by default. And that is, and we've discussed this a little bit before, R is going to put these categories in essentially alphabetical order. And so because of that then, j equal 1 is going to be healthy, j equal 2 is going to be scab, j equal 3 is going to be sprout because of putting in alphabetical order. So though that's how R is going to make the choices for the different numerical values for j. Now you can always use the function levels. And unfortunately, I thought I had taken care of that there. Unfortunately, there's this week 2, just from my revision of the notes over the summer, I had at one time been working with a data frame called week 2 that no longer exists in my program. And so if we just use the data frame called wheat, we can get the same result. So we use a levels function where type, that variable in the wheat data frame, corresponds to healthy scab or sprout. And we use levels here, and we can see, okay, this is going to be 1, this is going to be 2, this is going to be 3. And while this really is not of interest to us, does anyone know how you can tell R to use different levels? Or different, I guess, assign numbers differently? The way to do that is this. I could use the function called factor. Remember, R uses the terminology that a factor is basically a categorical variable. And if I said wheat $type, comma, levels, and then I'm going to combine together, and I could put, let's say, sprout here instead as first. And then I could put, let's say, scab, I could put healthy. And now R is going to recognize sprout as 1. As j equal 1. That I'm not going to ask you a question about on the test, but there's a number of times when you're doing a data analysis, typically for other kinds of data analysis, where you wouldn't like to have finer control over that stuff rather than go with the default, and that's how you can do it. And so what I could do is, let's say, create a new variable in my data frame called, let's say, type 2. So wheat $type 2 will create this new variable, and it's going to get the results from factor. The data is going to look exactly the same, just the ordering that R recognizes for these levels changes. Okay, so let's actually now estimate the model. If you remember, I told you before the function that we're going to use is multinomial. It's in the package called NNET. And I'm going to save the results into an object called mod.fit for the lack of a better name. Mod.fit stands for model fit. Gets the results from multinomial. And then I have kind of a syntax that we've seen before with the LM and GLM function. Formula equal. Here's my category. Here's my group variable type. $, I put in my independent variables. And then I say where my data is. And that should not be wheat 2. We have a little bit of information about the numerical iterative process. The main thing to pay attention to is this thing called converged. So that says, hey, everything worked. And then just like what we saw with the GLM function, if I say summary of mod.fit, I get a summary of the results from estimating the model. We have a table called coefficients. We've seen tables like this before. Notice we have something called scab. This is going to be j equal 2. And we have something called a row called sprout. That's going to be j equal 3. Why am I not seeing j equal 1 for healthy there? Well, because everything's being compared to healthy. So this intercept column, 30.54 in there, is beta hat 2, 0. If I look at the density, this is going to be beta hat 2, 2. The estimate of the corresponding betas from how I presented the model before. Let's see if I can do this nice little split screen so we can see that. Yeah, unfortunately, I did not get the ordering exactly the same there. So notice how I have class here, and then I have class there. I just didn't order it the same way. Not an important thing. Okay. So also, just to clarify, this 19.17 is beta hat 30. So a very simple question that I could ask on the final exam is, hey, why don't you estimate the model and then state what the estimated model is. And of course, you just look at the corresponding output to get the corresponding beta hats. And I think eventually I do actually state the model. There we go. There's the model right there. Again, there's 2 lines to the model in the statement. So we saw that 30.55 before. Okay. So let's talk about this class SRW. What does that mean? Now, in my actual code, notice I had class there. Yeah, let me just come over here to R. And if I do head wheat, we can see that class, again, is this categorical variable, has values of HRW and SRW. So, and we've kind of discussed this before, how does R now take into account that this is categorical, and in order to do math on it, I'm going to need to make this numeric. And so what R is going to do is create an indicator variable corresponding to class. Since it has levels of HRW and SRW, the HRW level is always going to be, or how should I put it? Actually write it out. R is going to create an indicator variable called class SRW, which is equal to 1 if it's the level of SRW, and it's going to be a value of 0 if it's going to be HRW. Why did R choose that versus the opposite? Well, R uses a set first level equal to 0 formulation whenever it creates indicator variables. Now, I am 95% confident that we've talked about indicator variables before in this class. If not, let me know. Okay. I'm not 100% confident, or I'm not close to 100% confident, but well, what happens if we had a categorical variable that had more than 2 levels to it? Have we talked about that? What? Yeah, we use dummy variables or indicator variables. So we have talked about it. Okay, good. So this is just simply a review here. Let's say if I have 4 levels for a categorical variable, A, B, C, and D. R is going to create 3 indicator variables. It's going to create them in this format here. If this variable is called temp, let's say, with levels A, B, C, and D in your data frame, R is going to create a indicator variable called temp B, one called temp C, and one called temp D, corresponding to X1, X2, and X3 respectively. But the way it will be shown in the output is temp B, C, and D. So I thought that we had talked about that stuff, and then I did a search through my notes, and I could not find where we had talked about it. Okay. So let's see some other stuff here in the output. We have a table called SCD period errors, or standard errors. So what this represents, for example, this right here, this 4.29, is the square root of the estimated variance of beta hat 20. The results in mod.fit are saved as a list. So there's a lot of information in there. And so you can say names mod.fit to actually see what's inside of there. One thing that in particular that's of interest to us is one called fitted.values. this corresponds to all the pi hats for every single observation. So if I do, let's say, head of mod.fit $fitted.values, we can see for observation 1, pi hat 1 is 0.855, pi hat 2 is 0.046, pi hat 3 is 0.098. And so if I wanted to, let's say, predict the corresponding grouping for observation 1, I would say healthy, because it has the highest probability. We'll talk more about that as we go along. Let's see here. Well, you might be interested in doing some kind of hypothesis test to examine, let's say, the importance of a particular variable. So let's say if I was interested in density, what I would do is the following hypothesis test. Oops. Density is represented in the model with two different betas because we had two different lines in the equation for it. And so I would be, the null hypothesis is that density is not important at all. So that would correspond to its corresponding beta to be equal to 0. The alternative hypothesis is the opposite of that, meaning that at least one of the betas does not equal 0. And so to do this test, I can we did this before with logistic regression. I can use this ANOVA function with the results that I saved, mod.fit, and is going to do a likelihood ratio test for these hypotheses. So if we look at the density line there, -2 log delta, our test statistic is 90.56. The p-value is less than 2.2 times 10 to the negative 16 power. So very, very small. So density is important. Well, why does that result make sense? We can go all the way back to our parallel coordinates plot. And we saw that at least for the scab, there seems to be some differences between them. Yeah, there's some overlap, but overall, it looks like, hey, density is playing a role in predicting is it scab or the others. And also, I guess I have some leftover circling here. We can see that the blacks tend to be a little bit higher than the reds at times. And so also that's another reason why we ended up rejecting the null hypothesis. This density looks like maybe it's playing a role in differentiating between healthy and sprout. Okay. And so we can see if we look at the other hypothesis tests as well, we're having some of the variables that appear to be important, others are not, or there's not sufficient evidence to indicate that they are important. Okay. So now let's focus more on this multinomial regression for prediction. That's really the main purpose of looking at this kind of model. We want to be able to predict the groups. And I've given you some information before, just a few minutes ago, about how to do that. So once we estimate the model, we want to come up with our pi hats. Okay. And here's how we've written the pi's before out, but now I just have hats on top of everything to indicate that they are estimates. And also I've said this too. We classify the observation into the population or the group, or predict the group corresponding to the largest estimated probability. So if pi hat 1 ended up being larger than all the other pi hats, we're going to predict that observation to be group 1. Let's see. Okay. Now, when we were doing logist regression, we talked about, a cutoff probability. Where maybe it might be, well, intuitively, use 0.5 to differentiate between the two groups. But you don't have to do that. You could use 0.4, you could use 0.1, you could use 0.9. And then that also led into the discussion about ROC curves. Now, you could use a little bit of a different criteria than what I've just introduced here for the multinomial regression models. I never see it used, though, in practice. So what that would mean is, let's say if you have, pi hat to be 0.4, pi hat to be 0.3, pi hat sub 2 to be 0.3, pi hat 3 to be 0.3. So based upon what I told you here, we would say classification, prediction would be group 1. But why not make a little change there, similar to what we talked about for the cutoff probabilities for logist regression? Maybe you could say, okay, in order to be group 1, it has to be at least 0.5. You could do that. But I've never really have seen that done actually in practice. In fact, I just haven't seen that done in practice. It would be interesting to examine that further to see if that could be helpful. I've seen only a little bit of research done with respect to ROC curves, where I guess essentially that they are making those kinds of changes, but it's only been a very little research of extending an ROC curve from the 2 grouping case to the 3 or more grouping case. So since there really isn't much done out there on this, I'm just going to continue focusing on, if we'll work with the group that has the highest estimated probability. That's how we make the decision. But also, let's take a look at, let's visualize what the model is giving us, because I think this can be helpful when one is making these predictions to understand what the model's doing. And so when we were doing logist regression, we looked at a plot like this, where we looked at the curve, looked something like that. Let's do now the equivalent here with multinomial regression. So let's just say we happen to know what the actual model is. We have, and this isn't with respect to the weak data. Let's say the actual model was this. I have 3 categories or 3 groups, and I simply want to plot it. Well, what function I would use in R to do this? Use the curve function. You can see my code in my corresponding program that I list here. And this is what I get. So on the y-axis, I have the corresponding pi. On the x-axis, this model only had one independent variable x. And so I've color-coded population 1 or group 1, population 2, population number 3. And so what we can see is this, that for values of x that are less than about 1.1, the highest probability will always be for group number 2. So any observations that have x less than 1.1 is always going to be population number 2. And if I draw another line here, for observations that have an x greater than about 1.25, it's always going to be predicted to be population number 1 or grouping 1. In between, it's going to be number 3 because it always has the highest probability. So this is just an interesting plot to see essentially what these models can do. Now, there can be situations where, let's say if I move this green line over to about, we'll move it over about 0.1 or 0.15 units. Notice what would happen there, and somehow you make adjustments to make sure everything still always adds up to 1 for the pi's. What can happen is that you might have particular groupings that never ever have a higher probability for any x. So you would never ever actually predict it to be a particular grouping. And we can see that we have a very narrow range here. In fact, in the original plot, very narrow range there for population number 3. Okay, so let's go back to the weak kernel data set. Let's talk about how we can do some of these calculations, let's say by hand, just to make sure that we understand the process. So, do a split screen again. Okay, so we want to find, let's say, for the first observation, what's the probability that it is healthy? We've actually already seen the value is 0.85. But how would we actually do the calculation itself? Well, we just put in the beta hats. We put in the x's corresponding to our model. So remember how we've talked about before that this 30.55 is beta hat 20 there. It ends up having a class of hard red winter wheat. So that's why we see a 0 from where I'm pointing right now. The moisture content is 12.02 for that first observation. In case I didn't say it, we're doing this for the first observation. And so this is then for, in the summation, little j equal 2. Then little j equal 3 is in what's done next over here. And if you go through all the math, you get 0.86. I've asked questions on a test that basically say, okay, I just want you to set up the equation and show me that you can do pi hat 1. You don't even have to do the full calculation. Just set up the calculation like that first line that I just have here. I've also asked, well, why don't you show me how you can set up pi hat 2, which will be scab for us. And so notice how the denominator remains exactly the same, only the numerator is going to change. And what's the numerator going to be? If I want to do, pi hat scab, well, the numerator is going to be that part right there. The denominator remains the same. Okay, so let's take a look at how we can do this, program in these equations in ARM. Okay, so the first thing that I'm going to do is I want to pull out of my data set all the actual values for that first observation. And we had just earlier done the head of wheat. And so, for example, we can see for the first observation, again, moisture has a 12.02 value. And notice in my code here, when I pulled out that first observation, we see 12.2 is the very last value in this vector. Also, notice I put a 0 into this vector, corresponding to class of hard red winter wheat. And then I put a leading 1 here because this is going to, when I do some math here, allow me to get the intercept term in my mathematical calculation. Okay. Now, mod.fit itself, I need to pull out what the beta hats are from it. And unfortunately, the only way that you can do that is use a function called coefficient, use a function called coefficients. If I do beta.hat here, there's all my beta hats. And so if I just want, let's say, the first row, I get the scab versus healthy beta hats. And so what I can do now is take my first observation, which is an x.vet, and I'm going to multiply it by the first row of beta.hat. And the way that R does this is going to simply line everything up and do the first element of beta.hat, first row, the first element of beta.hat times the first element of x.vet. Then does the same thing for the second of beta.hat and the second of x.vet. And this is what we get. So this leading one here, 1 times 30.54 is, of course, the same thing again. If I take, let's say, 12.0154 times 0.109, I get 1.31. So what I'm doing, this calculation here, I am doing this, oops, that's not, my eraser's not working. Hold on. The calculation I just did is this part here that I just circled. Now I want to combine everything. I want to add it up. So what do? I take the sum of that calculation, and I get negative 2.9. Then when I use the exponential function with it, I get 0.054, and that corresponds to this whole, let me do a highlighter, this whole calculation. Next, and so I call that scab dot part because it's the scab versus healthy comparison. Now I could go into a lot more detail about doing the sprout part as well. And that just simply corresponds to this right there. So notice how I'm using the second row. Now that I have what I call a scab part, sprout part, all I need to do to find the probability that the observation is healthy is take 1 over 1 plus the scab part plus the sprout part, and I get my corresponding pi hat for healthy. A lot of detail there. Make sure you go through it on your own just to make sure you can see how to do this. On a test, I could, instead of say set up the equation, I could say, okay, just do it in R with the equations. Now, I can do a very similar calculation for, let's say, pi hat 2, which would be pi hat dot scab. So I take the scab part divided by 1 plus scab part plus the sprout part. And I get 0.0464. Okay. So this matches up what we had before when I looked at the fitted dot values component of mod.fit. Now you can also get these probabilities by using a function that we've seen before as well called predict. So if I say predict mod.fit and also I include the argument type equal probs for probabilities, I get these same probabilities out. You'll see why using predict can actually be better than using fitted dot values very shortly. One also, I guess, reason with that is that instead of getting the probability, suppose I say type equal class for classification. In other words, predict the grouping. And so for the very first observation, what's returned is healthy, because healthy has the highest probability. Let's look at one particular observation that's in the data set. So we're going to look at kernel number 269. And rather than show you the actual numerical values immediately here, how about we take a look at it relative to the parallel coordinates plot? And so what I did, and we've seen how to do this before, is I did the parallel coordinates plot like usual. And then I say, let's do the parallel coordinates plot again, where I simply add it to the previous plot. So I say add equal true in my parcoord function call. But I only say, let's just plot observation 269. So for data, for the data argument, I would say data equal wheat, left bracket 269, comma, right bracket. And then I say, okay, let's really highlight it. So let's make the line thickness extra wide. And so this is what I get. So that's what 269 is. And so one reason why I point it out, because it actually has some interesting qualities here. It has the lowest weight. It has the second lowest size. Notice its density is kind of low relative to the other kernels as well. And so let's see if it can predict it right. So I say predict mod.fit, and then I'm going to include an argument, which we've seen with logistic regression, new data, where let's say I only want this particular observation predicted. So I say wheat 269. Type equal probs. This is what we get. Look at scab. Scab, that pi hat is very, very large. And so I would predict it to be a scab kernel. And so this is a correct prediction. But let's do these predictions now for all observations and do a summary of them. And so what I can do is I can go back to what we've seen before with a function called summarize.class to help us summarize what's going on. So if I say summarize.class, where my observed groupings is actually wheat, $type, classify corresponds to an object that I formed called classify. I apologize that I didn't go over that. There we go. I did go over it, but I just didn't say it. So when we use predict with type equal class, I put all the results into an object called classify. And so if I run this function, as we've done many times before, with what's observed and what's predicted, this is what I get. So we can see for healthy kernels, 74 times it predicted it right. 6 times it incorrectly predicted it as scab. 16 times it incorrectly predicted it as sprout. Now, based upon what we saw with the parallel coordinates plot, does that make sense that would happen? Yeah. We saw how the healthy kernels were much more separated from the scab kernels than they were from the sprout kernels. So again, whenever you do a statistical analysis, you want to see if things make sense. And based upon our previous work, yeah, this makes sense. For the scabs, 64 times you got it right, 19 times you got it wrong. For the sprout, 60 times you got it right, 19 times it was predicted as healthy instead, 17 times as scab. So notice how scab is in terms of, notice how sprout is kind of in between the healthy and the scab in terms of the results. Its ability to predict is lower there than it is for the other two. Again, relate this to what we were seeing in the parallel coordinates plot. Very often what we were seeing for density, sprouts tended to be more in between where the scab and the healthy were. And we can look at the proportions as well to see this. So healthy is 77% correct. Scab is 77% correct. Sprout is about 63% correct. The overall correctness of this model is 72%, 0.72. Now, what I'm showing you here is the results from resubstitution. Remember that. And we know there can be potential problems with that. Let's talk about now cross-validation. So to get cross-validation to work, I had to write my own function just like what I did with logistic regression. My function here is called CV2. Before we saw just CV. I had to write a completely new function because the way that the model or the information that multinomial gives me is a little bit different than what the GLM function for logistic regression gives me. So I had to do some extra stuff. There's still going to be a lot of similarities. And I'm just going to highlight some elements of this function. What I want to remind you is on your own, or what I want to remind you, first of all, is that, whenever you're presented with a new function, how do you determine, how everything's working inside that function for R? And so what you should do is as follows. Notice when I call this function here, CV2, I have two arguments, model, which is what we saw before with, using multinomial. And then I have an argument called data.set called wheat. And so what you can do is go up here to the function and run the guts of the function, or what's inside the function, with what those argument values are. So let's run that there. Oops, what did I do wrong? Okay, and then I can run it line by line to see what each line does. Do this on your own so that you have some sense of, well, what's actually going on inside of this function. Run it line by line by line. So after every line, look at what's pi.hat.cv, what is class.cv, and so on. But in terms of the big picture then, and that's what I want to talk about here, about what this function is doing. What it's going to do is it's going to remove one observation from the data set, estimate the model, and then try to predict what that observation that was removed, predict its corresponding classification, and also give me the corresponding pi hats. It's going to do that for the first observation. It's going to remove the first observation, do the calculations. It's going to put the first observation back in the data set, and now remove the second observation, do the calculations. This removal and putting back in is basically controlled by this for loop. So notice I do for R in 1 to n. We have n observations. So when I run this function then, this is what I get for there's two bits of information that's saved. The first one is the pi hats from cross-validation. So for the very first observation, pi hat 1, which would be for healthy, is 0.85. Pi hat 2 is 0.048. Pi hat 3 is 0.1. What did we have previously from using essentially resubstitution? Let me actually copy and paste this. Oops. Oh, shoot. Let's try that one more time. So before from resubstitution, I had 0.855. Now I have 0.851 essentially. So we can see we have similar results. We do have a sample size of 275. So that's why. Now, also what's returned is an object called classify, or a component to my list called classify, which then has the corresponding healthy scab or sprout predictions. And so if I run now summarize.class with the results from what was originally in my data set, with what cross-validation gives me, this is what I get. Let's see, before we were 77% correct for healthy. Now we are 74% correct. We were 77% correct for scab before. Now we're 72%. Scab is now 60% correct. Before we had 63%. Overall correctness has went down a little bit, 68.73%. Again, this is what we would expect with cross-validation typically. A little bit less. So, we've talked about how with these prediction methods, one method's not always going to be the best all the time. And so it's good to apply a number of different prediction methods and look to see which one does best for a data set. And so that's what I did here. I just don't give you all the details for the other methods. So what I did was I did linear discriminant analysis, I did quadratic discriminant analysis, I did nearest neighbor classification, and chose particular values of k using methods that we've talked about before. And then I use what ends up being a trellis plot here to summarize the results. And so let's focus on overall for now. Notice that multinomial has about, the x-axis is accuracy, has about the highest amount of accuracy. It's not that much higher than quadratic or linear discriminant analysis. We can see how these nearest neighbor classification methods, which end up having the smallest amount of assumptions, end up doing a little bit worse. We can also look at it, for each of these corresponding kernel types here. So for example, if we look at healthy, multinomial does the best, a little bit better than linear discriminant analysis. And so this kind of a plot then allows one to make a decision about, well, which method do I want to go with? If overall is what you're interested in, I'd probably go to multinomial. I'd probably be okay with some of the discriminant analysis too. But maybe, you're really interested in the healthy kernels, and then you might just look at the healthy part of this plot. Okay. Some additional considerations then for multinomial regression. We've already talked about the ROC curve part. You can do variable selection as well. The same problems that we've seen before occur here. And so that's why we didn't necessarily discuss that. There are other models similar to a multinomial regression model that can be used here in terms of like a regression setting. So for example, one kind of model, and you're not responsible for this, but I would say the second most popular kind of model is called a proportional odds regression model. This can be useful in situations where you have some kind of, let's say, ordering amongst your categories in terms of, let's say, well, I wouldn't say, I don't want to say rank. I don't want to say that. But let's say we were trying to predict political party. We had some other data set we want to predict political party. And, you can think of it in the U.S., let's think of Democrat, Republican, Independent. Where independent's kind of in between Democrat and Republican. So you have, let's say, D, I, R. Notice there's an ordering there in terms of what one would typically think of in terms of their political views. From liberal to conservative. And so if you have that, then you could take advantage of that ordering by constructing a proportional odds regression model. Now, in our particular setting that we were looking at for the wheat data, we definitely have one category that is the most preferred, healthy. And to some respect, you could say that I would prefer sprout over a diseased kernel, scab. And so you can say I have an ordering of scab, sprout, healthy. It's, at least when I originally did this this consulting problem, I did not do that. I thought of that ideal later. It's still, I think, somewhat questionable to do it, but you could. And so if you have some kind of ordering like that, what you can do is, again, take advantage of that ordering. And you can think of this in terms of like a logistic regression model. But instead of, let's say, modeling the probability of success inside that logit, we have the probability that you're in category, let's say, J or less. So you have now, you're modeling cumulative probabilities instead of just probability of one category. And so what we can see here is what looks like a logistic regression model otherwise. If you have that model formulation, you can eventually still come up with pi hats for each category itself. And then, again, predict a particular grouping based upon which has the highest pi hat. If you want to know more about proportional odds regression models, I do have a little bit in my corresponding program. Again, you're not responsible for it, but also you can take a look at my categorical data analysis book. In the end, for this particular setting, the overall classification rate isn't better than what we have with the multinomial regression model. Okay. This last note. There can be times, it doesn't happen a whole lot, but there can be times where R will say you have convergence when you could have used a few more iterations. For our class, you don't have to worry about it. Obviously, we're at the end of the semester. It would take me some time to explain what's happening, why it occurs. But let's say if outside of this class you end up wanting to use a multinomial regression model. What I recommend that you do is you take a look at the max it argument in multinom, which allows you to do more iterations, and also to make a decision about when you have actually converged. There is an argument called rel-tol, which stands for relative tolerance. In terms of, if you remember when we were talking about these iterative methods, you look at the beta hats for, let's say, iteration 1, and then you look at the iteration 2 beta hats. If they're close to one another, you say converge. If they're not, you keep on going, and you keep on looking how far apart they are. That rel-tol basically controls, what you're looking at in terms of how far apart they can be, or how close they need to be to converge. And if you simply make this corresponding numerical value lower, you won't have a problem with convergence. If you want to know more information about that, my categorical data analysis book does talk about it. Okay. Sorry to have to kind of just go over that in a brief detail. Okay, so we're basically out of time here. So what's next in our class? Obviously, I'll have my office hours after class. Thursday, we actually will not need to continue with multinomial regression because we just finished it. I will briefly talk about doing hypothesis tests for mean vectors. You will not be tested over it, though, because we're out of time in the semester. Okay, so I'll just briefly talk about it. It's a topic that you often see in these kinds of classes. It's just not as important as it once was. But it's kind of interesting, because it's an extension of something that you've seen before. We will spend the remainder of the class period simply reviewing for the final. So if you have questions, please bring them. I'll talk about the details about what to expect on the final. We will review some of the material as well. The final exam, again, is Thursday, December 14th at 7:30 a.m. Are there any questions? Okay, that's all for today.